Okay, I'm back, and so now I want you to go to the internet and then type in Physics Classroom Simple Wave Simulator. And then that is what you're going to see. And so I have already gone to that website, and so here it is. And so we want to discuss some of the features of this website. So this could be representing an ocean wave. And you see that it's going up and down at a certain frequency. And so that is right over here. This is the display of the frequency in hertz. You can also control the frequency of it by changing that. Okay, so here's the how to control the frequency, and then if you change this, then it changes this number up here. Okay, now the period, if you recall from our notes, the period is given by a letter T, or Greek letter T, and it is going to be equal to 1 over the frequency. Now, you'll notice that in some of these simulations, they're going to use the letter F for frequency, but I like to use this symbol here that's called nu. And so that's the Greek letter N. And this is how the period of a wave is related to its frequency. So you should notice that while the frequency is small, the period is large. And so that's a direct relationship from this thing here. Now we're not really going to do much with the period, but I just want you to be aware of that. Okay, then you've got the speed of the wave, and it's set for 100 centimeters per second. So that's 1 meter per second. And that's a pretty fast wave. But you can change the speed of the wave by with this slider here if you want to. And then you've got the wavelength of the wave, and so that's going to be the letter lambda. So wavelength is going to be this letter here, lambda, and so that's going to be the distance from a crest to a crest, or it could be the distance from a trough to a trough, or it could be the distance from the midpoint to the midpoint where it repeats itself again. And then over here you've got the amplitude, so this is going to be the size of the wave. So you might want to just kind of play around with these three things and then see what happens when you do that. Alright, so now let's go back to the lab here, and then it says to click on Show Waves as Sound. So now let's go back to the lab, and we're going to click on this thing here, Show Waves as Sound. Alright, now it's still showing the original wave. So actually, let me click on this again. Okay, so you see there's that green thing. Okay, now that green thing is this blue thing right here. And now we can pause the simulation so that you can look at this in more detail. But what I want you to notice is the green dots represent air molecules. And then look at places where this blue thing is at its maximum, and then see what the green dots do at that particular point. And then the blue line is going to have its minimum where it is right here in the middle. So it has its maximum up here, has a maximum down here, and then in the middle that's where it's going to have the minimum amplitude. And then look at what happens to the green dots when the amplitude is a minimum. So I'm looking for words like spread out or compressed. So those are the words that I'm looking for in the lab. And then this should remind you of a particular kind of wave. So look at what those green dots are doing, and then compare it to, so let's go back to the lab, and then compare it to this picture up here of the longitudinal and the transverse waves, and then those green dots are doing one of those two things. So see if you can figure out what that is. Okay, so you're going to select the correct statements. So either highlight most concentrated or least concentrated, and do it in red so that I can tell what you wrote down, and then do the same thing for this statement down here. Okay, then we're going to click on real time and compare the green dots to the two ways that a slinky can be moved. So I just mentioned that. And then are sound waves transverse or are they longitudinal? Now, you figure out what that answer is before you go to the internet and look it up on AI. So if you just are, looking up these answers on the internet and then writing it down, you're not learning anything. So make a prediction first, and then it's okay to go to the internet and see if your answer was correct. Okay, now we're going to fill in this table here. Write down the measured frequency, the measured wavelength, and then the speed of your waves. So if we go back to the simulation here, okay, you can write down the frequency, you can write down the wave speed, and you can write down the wavelength. So you can write down all of that information from the simulation in this chart. So that leaves you with this last one, calculated speed of the wave. Now you know what the speed of the wave is, okay, but we want to calculate the speed of the wave. And in order to do that, we're going to use this formula. Now be very careful, because if you're not paying attention, you might get one of those letters incorrect. So it's V for velocity or speed is equal to wavelength times frequency. So remember that in some textbooks they're going to use the letter F for the frequency. Okay, but that's the formula that you're going to use to calculate the speed of the wave, and then hopefully it will be the exact same number as this one up here. So these two numbers should be the same. Okay, now it says to increase the frequency and complete the following statement. So do this. If the frequency of a wave increases, then its wavelength does what? Now you should be able to predict that using this formula right here, because the speed is not changing. The speed of the wave is the same, and what we're going to do is we're going to increase the frequency. So the frequency here is going to get larger, and the question is, what does this thing do in order to compensate? Okay, and so remember that, for example, 1 times 4 is equal to 4, but 4 times 1 is equal to 4. So do you see that if one number gets big, then the other number does something in order to compensate? All right, let's take a break, and when we come back, we are going to talk about standing waves.